Hello, everybody. We are going to start a webinar in a few moments from now. Thank you. Hello, everybody. Welcome to another webinar, part series of up to date about the post processors. And this will be the part 3. And my name is Daniel. And today the presenter will be Vukasin Nikolic. And before he opened his presentation, and I'm going to share you a few things and to say thank you to all who contributed the in this on this webinars. Okay, so first I'm going to show you, as the previous webinars, we are also recording also this one, and the recordings you can, of course, you can find on SolidCAM.com. And many of you also ask us, okay, where you can find this, and you can go to the webinar section over here. You can go to the webinars recording. You can go to the latest webinars. And here you will be able to find also the video. You can download them. You can go to and download the webinar content, anything that you need. Of course, like with the previous one, I can just click on it. And my suggestion to all of you is to not play it inside the SolidCAM website, but to go to the YouTube over here. Just jump over there. And like with the previous, you will be able to see the timeline here, and you can just easily jump to the particular subject that we actually discussed, just clicking on it, and it will jump there. Now, in additional, I promised last time that I will put all the SolidCAM statics application together with the presentation tool that I also used in my part 1 webinar. You can find the links here. Okay, these links will be available on all videos that we are uploading in the future. And that's it. The few things about the forum itself, forum.solidcam.com. You can go to the section of the post processors, where the same links you will be able to find also in this topic over here. But we also for all of you who are, who these webinars are pretty advanced, we also cover, all our webinars we are putting in a specific topic that you can see over here. And here you can see all recorded webinars that we have done in SolidCAM so far. And the one that we are now covering is at the very bottom of it. Besides of that one, we have here up-to-date post-processor webinar series, where I also ask in the part 1, part 2, and now in part 3 for any kind of questions that you have, guys. If you have any particular subject that what you want to be covered besides of the mentioned one, please write us down here. I can see that many of you activate. I'm really glad that this works very well. So just please don't be shy, just go ahead there and write us your suggestions, comments there below. Of course, also small detail with all of these subjects, you also have the hyperlink over here, so it will also guide you towards the recordings itself. That's it from my side. I will now give I will make a presenter, Vukasin. He will be the main presenter today, as I said. So, Vukasin, good luck. Show us what you got.
Okay, thank you, Daniel. I hope everybody can see my screen and hear me. as Daniel said, you can check the forum for the topics we'll be covering today, but also I would like to summarize it in a in a minute. So we will be talking about the changes in arcs, new variables, some main differences between the older versions, mainly 2020 and now 2021. We'll be covering the compensation and also the new get functions that are used to handle holders, handle their connection points, stations, and etc. So I would like to start off with a simple topic, that is the approximate arcs by lines. Many of you already know about this option, when we use it, why we use it. It can be used on machines that mainly don't support arcs, but you handle that by the VMID. Some machines cannot handle arcs in 3D, so you would like to turn this on. On mill-turn machines that don't have the interpolation cycles, they cannot do the C-axis milling with the fourth axis with the arc. So any of those cases, use this option. Now, in the past, we could not see if this option is turned on or turned off, except for the appearance of the arc procedure. But now, if I generate trace 5 and search for that function, so we are in channel 2, we don't need the channel 2, we need the channel 1. I will search for the, not that, but arc approximate. Okay, here it is. Now, I'd like to mention that it is in the start of job procedure and also in call proc procedure if the procedures are turned on. So you can see arc approximate, the value is 0. That is because we did not turn it on. Now, you can say if it is a particular type of job, if it's a job that doesn't support the arcs, you can say if arc approximate is 0, please print a note to the CAM programmer, please turn on arcs in job this and this. So that is one of the use cases. Now, of course, I will close this, I will turn it on, I will say, okay, it's 0.01. If I save it, again, trace 5, channel 1, okay. If I search now, let's search for start of job. Okay, start of job. Let's go to the bottom of the start of job. And here it is, arc approximate is 0.01. So maybe you need this value and knowing that the function is turned on. Maybe you want to turn on the smooth function. You can say if arc approximate is not equal 0, turn on the smooth function with this tolerance. And that would be it. It is a often requested variable, and now you have it. I'm sure that you will know how to use it. Now, the next thing are some changes between the generation of arc in the SolidCAM 2020 and 2021. Now, if I open the VMID, and if I go to the controller definition, arc execution definition, and many of you may notice that we are missing an option. Below this option, there was another one. Now, if I open the post-processor for the same machine, but in the 2020 version, and if let me put this down, go to the controller definition, arc execution, you can see that we have arcs in main planes only. Now, this is removed from 2021, and it is operating by the next rules. Now, let me show you an algorithm. So, first question is, can we define the working plane? How do you know that? Well, if you have defined the tilting plane definition inside the VMID, then you can define a working plane. It, yes, gets the arc in trace. If it is no, but the arc is in one of the main planes of the submachine coordinate system or the virtual Mac, then it can generate arcs in trace or generate only lines. Now, how can you know if you have a working plane defined or if the arc is in one of the main planes? Well, let me first explain what is a submachine coordinate system, or what is a virtual Mac. Now, if I go to the SolidCAM help, if I search for virtual Mac, the last topic will tell you the best. It is the correct definition. So virtual Mac is when you take the coordinate system of the submachine and put it in the origin of the job Mac. If I show you that on our part, if I open the setup, in setup, sorry, we have our Mac 1 position 1. If I generate the machine preview, you can see that this is our virtual Mac, okay? That is our virtual Mac. So it's the coordinate system of the submachine that is taken into the Mac 1 position 1 origin point. Now, if I were to open the operation that I've shown here and generate the machine preview for it, you can see the following. First, this is the Mac 1 position 1, and it is oriented as in the setup that I have shown. But we have an option here that shows the position coordinate system. And you can see the coordinate system of the position that is used. And please notice that the orientation of the coordinate system here is not the same as in the Mac 1. So it means you have a tilted plane defined. So here we will, of course, get the arcs, and they will be in the XY plane. Now, if the tilted plane is not defined, the position coordinate system would be in the same point, but it would maintain the orientation of the original Mac. So that is how you can quickly and easily check it inside the SolidCAM machine preview. Everything is kinematic, and you should know by looking at it what to expect inside G-code. So if I go back to the picture, so can we define the working plane? You can check by the preview. If we can, you will get arcs and trace. If you cannot, but the arc is in one of the main planes of the original coordinate system that I've shown, or the virtual Mac, then you will again get arcs and trace. If not, SolidCAM will automatically approximate arc by lines. And that would be it for that. Now, what's next and what's changed inside arcs? Let me load a comparison file between the SolidCAM 2020 and 2021. So I have it here. I will just search for the arc procedure, and let me zoom in a bit. So this is the arc. And the first thing you may see missing is a line in the 2020 version. So the left one is 2020, right one is 2021. You see there's a line missing. This is a new variable that I will explain in a minute, but the other change is that we have added change bits to the post coordinate set and L post coordinate set. So X center relative, Y center, Z center relative will have change bits inside 2021. Also, the L center and L center relative will have change bits. So this is just to prevent the printing of the non-changed or zero value variables. And a new variable that is added is the center absolute. Now, you may say, but we already had that. And yes, it is right above, but this is an arc generated for the turning job. And you can see that we have X and Y center, but turning jobs are done in the ZX plane. And that is why it is developed to have the new variables in order not to break posts with the old ones. And I will show you what was the logic behind the X and Y center, even though it was in the ZX plane. Now, if I go back to SolidCAM, if I open a turning job and I would go to the plane. Now let me use this, minimize it. Okay, now let's take a look at the 2021 version. So like I said, the job is in the ZX plane. But if you take a look at the coordinate system below, this is how SolidCAM looks at this job. I don't say that this is a coincidence that it matched up with the SolidWorks coordinate system, but it's a perfect representation of how SolidCAM looks at it. So you can see Z axis is matching the x-axis. So we are getting the x minus 25.6. It is matching the x1, the z value, but it should be here. And this is why the new variable works. So, and also the x-axis that is inside the real job is looked at as y. So y value is in the x center absolute. So with it like this, you don't have to think about if you are in turning job, if you are in milling job, you know that you will always get the correct values. So we did not remove the old ones, we just add a new one. So there's no need to update old posts. And one thing I would like to mention also about ARCs is that it is being worked on to add ARC support to the turbo operation. So turbo HSM and HSR are actively being worked on to add ARC support, since this is much requested from our sellers and clients. Now that would be it for the ARCs. I would like now to transition to the changes inside the compensation. Now, the first change that that happened not between 2021 and 2020, but after the 2021 release is some of you probably noticed that the side O variable that was responsible for the compensation inside the opus set was not working after the release of 2021. It is fixed now in 2021 SP2 and later. And you should know that if you had any workarounds or anything that was handling that bug, you can remove them and just insert the side O inside the compensation procedure, and it will work fine. Now let me just check if I have compensation turned on inside this operation. I do. Now let me generate it and try to explain another change that happened. So this is inside the channel 1. Okay, so this one I will close this and this, and let's search for the compensation procedure. Here it is. Now, as you probably know, we have side O, and we also have a new variable. It is side H. What is its main purpose? Well, side O and side H variables are very similar. Both of them reference the virtual MAC or the submachine coordinate system, like I said. So each of them will take a look at that coordinate system. As you know, probably, side O is used when you have a tilted plane definition. So if you are working in plane, let's say it's a table machine, you have the plane rotation cycle, you have rotated the plane, you are in the XY plane, you would use side. Maybe you are on a mill turn machine with the B axis, like this end takes from the example is. Okay, again, you can rotate the plane and you can use the side. But if you are working on a mill turn machine with a rotary turret, or a Swiss type machine, or just a regular turning machine, you should use the side O, because it is referencing that submachine coordinate system and is always relative to it. Now, side H can be used for the same purpose, but side H has one difference between the side O that I will show you on another example. Now, let me close this project and let me open a different one. Now, I will transition to a Haas 3-axis milling machine, but with an angular head. Now, this is where the side H can be useful. Now, let me just check the VMID first. Let's check the tilted plane definition, and it is set to none. Of course, it's a 3-axis machine, it just has the angular head. So I will close. Yes, I will save, even though I didn't change anything. And let me load a operation. I think it's this one. Yeah, this one can be used, or maybe, yeah, this one is even better. So I have this operation and it's in a position. Now, firstly, let's do, like I said, let me show you an example. How can you check if you have a tilted plane definition? We have our angular head. Let me zoom in and let me show the position. And here we go. Z, Z, X, X, and Y, they are all in the same direction. The origin point has changed, but the orientation is exactly the same. And that is how you know that you don't have a tilted plane definition defined. So here, you can expect everything that is related to other coordinate sets that are not LPOS or POS. So let me show you what is shown now inside the compensation. Let's generate trace 5 again. We have only one channel here, so let's go to comp. Here it is. So you will see they all have values. They are referencing the orientation of the coordinate system is the same, so they are showing the same value. Now let's go to a different operation. I will generate both of them. So we have an operation here, I think. Yes. So this operation is at a 45-degree angle. So it will not be in any of the main planes. Now let me just select both of them. And again, generate trace 5. Okay. Let's search for compensation. Okay, like we shown, it is side left. It is turning it off after the operation. But take a look at this. We have errors. Why? Well, our machine cannot define tilting of the plane, and compensation cannot be done if it is not in a plane. So we get errors. The value of the error should be -9999. So if you can search your compensation procedure, if error, if any of the sides is equal to this, then display a warning to the CAM programmer to turn off the compensation. Maybe just don't print out the compensation, but notify the user or something like that. So let me add the tilting of the plane to the pod processor, even though the machine cannot support it. Let me add it just to show you the difference. So I will just transition from one to another, so it will automatically assign a order or rotation. I will save it. Now let's generate for both of these. I go G-code, generate. Let's use trace 5 again. Search for compensation. Okay. Again, we are in a main plane, so we get the values for everyone. This is the turning off of the compensation. And now you see side and side O have become defined, or they got a value, but side H got an error. Why is that? Well, this is the only difference between side O and side H, is that the error for side H is also displayed even though if we have tilted plane definition, but we are not in the main plane. So side H will only have a value inside the main plane, let's say like that, of the submachine coordinate system or the virtual mech. Now, where you can use this, let's say you have a table machine and you have the tilting of the plane and you rotate a part, use the tilting of the part, but still are not inside one of the main planes. Then only side H will tell you that. Let's say you're using an angular head on a milling machine that has the tilting of the plane, and your position doesn't end up in one of the main planes. You will use side H to check for that. And that's the main purpose. That's the main difference between side O and side H. Otherwise, they work identically. Again, the error value for you to check is -9999. Please note that this value is in the DV and should be in the next version. Now, let me close this code. Let me return the tilting of the plane to the non-defined, and that would be it for the compensations. Now, the next topic is probably more interesting to you because now we are transitioning to the get functions. The first get function I would like to show you, and I will open the GPP tool help. Let me go back from here. It is the getting the number of components. Now, what does this function do? It shows us, or it counts the number of tool components inside a tool assembly. So let's say, like in this example, we have the cutter, number 1, shank, number 2, holder, number 3. Now you see that tool item is skipped. I would like to note that this function is extended and it has another parameter that tells you if the tool item is counted or not. And I'm using the DV version, and I will show you how it works. And it should be inside the documentation and also the official version by the next release. So we have 1, 2, 3. If we are counting this 4, and then station 5, or if we are not, then just 4 items. Now let me open SolidCAM and let's go to the toolkit. I won't use this one, but let's use tool 15, and let me open the advanced view and let's count. So we have the cutter or the drill. So 1, 2, 3, 4, 5, 6, or 5 if we are not counting this. So let me show you how this works, and that would be the easiest way to do it. Let me go back to help. Let me just copy all of this since it will work. Let's open the post processor. We use tool 15, okay. Yes, I want to save the changes. Let me open the post. Okay, now Haas, okay. I will delete this since I played a bit with it. Okay, now I have copied it from the help. Yep, let's go to the post processor. Let me add a separator so we know where to look for. Open the apostrophes, a bracket. Let's go like this. Just I will duplicate it and let's paste it. Since I pasted from the help file, it is adding some lines. Let's format and okay. But the one I've copied has only one parameter, and if I try to generate now, I will get an error. So I will add a comma and I will say 0. That will say, okay, don't count the tool item, or I can say 1. Let's go with 0. Okay, and it will say get number of tool components, assign that number to this, and that's it. So it will print out number of tool components for tool number. The tool we chose is this. Now let me save this. Let's go to SolidCAM. We can close this. And we use tool number 15, so it is this one. And let's go. G-code, generate. Okay, and here it is. Number of tool components for tool 15 is 5. Like we counted, it is 5 without the tool item and 6 with it. So this is the use of that function. Now, how can you use it practically? Well, let's say you are working on important mold parts, and you know that your assemblies need to have holders, shanks, and everything in order to have the correct output, in order to have the correct simulation. So you can check with this. You know that you have the station, you have the cutter, so that's 2 elements. If you're counting the tool tool element also, so that's 3 minimum. So if the number is less than, let's say 4, you should know that your CAM programmer forgot to include the holder, the shank, adapter, everything like that. So you can print out a message, number of tool components is less than, let's say 4, please check your tool assemblies, or something like that. Now, the second use of it can be if you overlap this function with another function that I want to show you. So right below it, it is get tool component name. Now it will count, it will name all of the components inside the tool assembly. Again, this function is also extended. It has another parameter that is the same as in the previous function, and it will either count this or not. So I will go to it. So let's copy all of it again. Okay. And here it is using a while loop in order to print out all the elements, or you can use just a number of the tool element. Let's say I want to use the element number 2. You can use that also. So let me copy it to here. And again, we have empty lines. So I will sort this out. Okay, okay. And let me format it. Now, again, we have the number of tool components. I will delete this here. We are getting the number of tool components also here. So that will be removed. Let me just remove this. So this is the first function and this is the second one. Now, again, I just need to remember that I need to add this. So we haven't counted the tool tool item. Let's now count it out. So let's set here 1. I will save it. And let's go back to SolidCAM. Let's generate G-code. And here it is. So as I have transferred to 1, it is now counting the tool element also. So it's 6. And here is the cutter, the shank, one part of the holder, the adapter of the holder, the tool item, and the station. Now, let me just leave a quick note. If I close this, and if we open the toolkit, and here is the tool 15, you can rename this. So this is a example tool item. Okay, I will save and exit. I will go back to the operation, generate the G code again, and let's see what we got. So trace 5. And here you see, we have the example tool item. Many of you didn't know probably that you can rename it, and we got some questions. So I wanted to know that. And that's it. Now, where you can use this function, let's say you want to rule out only the name of the example tool item. So you know that the tool item comes always after the station. You can say, okay, maximum number of tool components is 6. That is my station. I want to print out the name of the element before that station. So let's do this. It's nice and easy. All right. Now, how can we edit this? We don't need a while loop anymore. Okay. We don't need this. We don't need this. Okay, sorry. Now, we are just getting the number, the name of the component. We don't need this either because we want to say exactly which component we want. So let's say I want the component that is maximum number of tool components -1. That would be example tool item. And let's say this tool item name is, and I will delete everything. And this, okay. And it should print out the component name. Let me just format it. Let's generate the G code and hope that we didn't make some small mistake. Nope, everything's good. So tool item name is example tool item. And this is one of the many use cases. You can have a million of them. You can be creative, make tool lists, make whatever you want. And the most important thing is that this is a get function. Get functions work anywhere inside the code. So if you decide that you want to print in start of job, something that is printed after start of job, you can have the data. For other things, without the get functions, you had to be creative and lose much more time and type much more code in order to get to the same result. So this is a nice and easy way to do it. Now, staying in the topic of get tool functions and holders and similar things, I want to show you the next function. So if we go to the tool help, we have the base geometry options. Now, what do they do? So we can have get the base geometry name. Now, first you may ask, what is the base geometry? Well, base geometry is a holder element that is, as the name says, marked as base geometry. Now, let me open the toolkit. Let's stay at this example of tool number 15. Now, here I have my base geometry selected. You can find it in the properties page, and only if you are in the holder item. If I go to the shank, there's nothing. So only the holders. Now, let me go back to the help file. What does this function return? The base geometry name tells us the name of the joint closest to the tool on a holder that is marked as base geometry. So this can confuse you. So you have a holder marked, you have a few holders marked as base geometry, and the joint name that will be used is on the holder that is closest to the tool. Now this would be much more easier to show an example. So if I click for an example, it leads us to the other base geometry function. It says get base geometry position. What it does, we get an X, Y, and Z value from the spindle tool station to the closest joint to the tool on a holder marked as base geometry. Again, this is the example I'll be also using. So we have two elements as holders, and they are both marked as base geometry. So it can use the joint 1 of the IDX geometry or the joint 007 of the TA geometry. Now, but it will use this one because it is closest to the tool. So this joint is the joint 007, and it is closest to the tool. So we get the distance from here to the tool station. Now, again, everything is much prettier with an example. So I will copy everything and go back to the post-processor. Now let me just clean this up a bit. I will duplicate this line and let's paste it. Let's clean it up. So we have this. Okay. Now, also you can see here that we have the joint name. So we can check which joint is used as base geometry in this measuring. So the function is, as in the example, we'll have result. So if the result is 1, the function was successful. If not, you'll get an error and an error message. But let's see, we have a tool tag, so it's a unique tool number. We have 3 variables that will store the distance, and later the printing of the distances. If I format it, it's all okay. I just need to call this procedure inside start of job or anywhere that I would like. Again, this is a get function. It will work with wherever inside the generation procedure. So call get the user base geometry, and let's go back to SolidCAM. Now, how do I know what should we get? I will close this. So both of the holders will be marked as base geometry. So if I focus, we have the upper part, and its distance from the station is 77. Okay, and we have this one, and its distance in Z is 156, and in X is 70. Now, please note that this is a positive value, but the X looking at the coordinate system of the station should be negative. And let's see what do we get as a result. So I will just save and exit. I will go back to this operation, generate the G code, and here we go. So distance minus 70. Like I said, it is looking at the coordinate system of the station. So in Y we have 0, and in Z it is the 77 that we had on the first joint and 156 that we had on the second joint. So it adds it up in order to tell us how far is the joint from the station coordinate system. Now we got the name, it's a test joint, or in the example in the help file is joint 007. And you also get the name and how this function works. Now, again, some of you may ask, why do I need this? Well, on angular heads, some machines cannot offset their tools in 3-axis, only in Z. Now, maybe you need to know how far is the tool mounting point from the station coordinate system. Now, this function will return. But then also show a function that shows us the exact distance from the tooltip to the station coordinate system also, and it can be used as well. That would be it for the base geometry functions. I would now like to cover the important variable that was added for the mill-turn machines, for Swiss type machines, and also for the support of angular heads. That function is called the all machine plane. Now, it is being used for some time now, and it's basically the machine plane inside that OPOS coordinate set or the submachine coordinate system, according to the submachine coordinate system. Now, how you can check it? Well, let's say, as we said, this machine doesn't have a tilting of the plane. Now, if we check the machine preview, and if I show the position, it will show that we are inside the Z, Y plane. Now, if we had tilting of the plane, this Z direction would be as X. So let me show you that. So I will again define it, just toggle this back and forth. Okay, let's show machine preview. Okay, and now if I zoom in, if I show it, now if you take a look at this, our machine plane is XY. But if you take a look at the submachine coordinate system or the virtual MAC in this case, and if I generate G code, we can check this. Okay, and now let's search for, let's go with all machine plane. Now we have the rotate to plane, or you can find it inside the start to job. But like I said, machine plane is XY. And you can see that here. But the all machine plane is YZ. So it is a reference to the virtual MAC that has the orientation of the submachine coordinate system. And this function is useful, okay, for the angular heads, but the much better use case scenario and the use for where it really saves us some time is the mill-turn machines and the Swiss type machines. Now I will close this. I will just revert back to the non-kinematic, non-rotating plane. And let me load another project that is a Swiss type project. Now, on these machines, they for sure don't have tilting of the plane for the linear holders. Mill-turn machines don't have the tilting of the plane for the tools on the radial turrets. So you need this variable in order to show to know the correct plane. If I open the post-processor for this machine, okay, I'm here in the machine plane. You can see, okay, for turning, we have the plane that is 18 always, but for milling, you have only let's say 7 lines of code that tell you what is the machine plane. So all machine plane is equal XY, it is 17, YZ 19, ZX 18. And that's it. So you can disregard this. This is the saving of the values, or for if the rotary option is turned on. But if I load the old post and search for the same user machine plane, so let me find the user machine plane. Okay, so it is here. Okay, it's always the last one for sure. Yeah. So this is the procedure. Now, if you take a look at this part of the code, it's not much longer. And it has a different logic. It is depending on the submachine or the tool direction in station. Now, if I search for this, here it is. We have a whole procedure that tells us what is the tool direction in station and what's the angle around the specific axis. So you had to know if the tool is rotated around a specific axis, then it is one plane. If it's a different value, then it's the other plane. But it is, if you agree with me, this is much more elegant, much more simple, and much more easier to check. If you check back on where we found this variable, it says if the value, you need to know that this is the y-axis, and if it's not 90, then its tool is not mounted inside in the z direction. You had to know much more and to concentrate to it was harder to debug, opposite to this, which is just 7 lines of code, simple, easy to read, and easy to figure out. Now, as I said, all machine plane reference to the virtual MAC and the submachine coordinate system. And as we were at the handling of the planes and everything inside the Swiss type machines, I would like to show you another useful function and show you the brochure for a star machine. So I will go to the read mode, and we have the star machine from the example I was showing. And if I scroll down, you will see this type of holder. So I'm not sure how well you can see, but this holder is a multi-tool holder, and it mounts to one tool station. So let me scroll down. You can see this holder is now a radial holder, and you can see the example they have. We have two holders here, but what's the main catch? Well, they are mounted on a single tool station. Now you have the tool number, but you also have the subtool number. And if you check this, this is the example of that holder. And we have the holder that is mounted on the T34 station, but it has 3 substations. Now it has the station number 21, 22, 23. And also it can be for main spindle or the back spindle. How do we call this type of tool? Well, you need to call T34, that will align it in y-axis, and then 23. That tells us what substation is being used, and it knows how far it should go down in x. Now, if I open let me open the toolkit, and let me close this, hide this, and open the machine preview. And you can see right here. Now, if I just call the tool as T3400, the machine will just go in y-axis and align itself with the guide bush. So this is what you get, and it doesn't know which subtool item is used. Now, once you call T34, let's say 23, which is at the top, it will use its x-axis and then align itself as it should. Now, how this was done inside SolidCAM 2020, you had the tool station here at the tool number 34. That was a dummy tool station to mount the holder to. And then you had a station for each of the subtool items. Now in 2020, we only have one station. As you can see here, this is only one station. Now it's advanced view, but subtool items are handled with a get function. So Let me minimize this, and you can see I have our holder here. And let me show this preview. And you can see it has 6 joints, 3 for each spindle. So we have 21A, 22A, and 23A. These are on the left side, and the B index is on the right side. Now, how do we know on which one of them the tool is mounted? Well, if I go to the help, if I find is joint name exist. Now, what does this function do? It returns the operation if a specific joint name is in a selected tool holder system. So I will tell it, for the tool number 34, do we have a joint that is TXX21A? And the function will return true or false. Now, according to that, you can implement it in mainly the Swiss type machines. You can just be careful to name your joints as you implemented them in the GPP, or you need to teach your technician or the guy that is training the clients or the client itself how to name the joints when creating their new STL holders. But after that, you have a system that is easy and simple to handle the substation numbers inside the GPP. So let me show you how it works. I will just copy the format and let me open the post. Let's close this. So here it's T34. So it's the first operation. Open the post processor. So we are in the machine plane. I know that the change tool procedure is handling this, and here it is. So let me just zoom in a bit. We have the user change tool, and this is the tool number. So we're using tool positioning turret to get the tool number and multiplying it by 100. Why we are doing this? Well, to get the 3400 output. So we know 3400. Now let me just generate G code and let's see what we get right now. If I generate G code for the first one, okay, let's go with trace 5. Okay, this is the channel 2, we don't need that. This is the channel 1. So let's scroll down, and here it is. We have the tool number 3400. We don't have the substation number, and the linear turret will just align itself in the y-axis. Now, we need to implement the substation number. Also, the wire offset here is called number T34. So we need to change that also. If I go back to the post processor, we need to add here something like, let's say, substation number. But let me delete this and format it properly. First, we will need the get function to get that substation number. So I will create a procedure. Let's call it user substation number. Okay, and we need an argument. Why? Well, we need to feed the value out of the procedure. So I will call it a local IL substation number, and I will declare it inside the change tool. So I will go with local integer and use this. So, and also we will use it here. Now I need to declare a procedure, and it's a argument called. So, okay, let's go here. Let's go and p, but we need to say it is an integer. So I have copied the format. Let's go back and let's say if is joint name exists with a tool tag. In this case, it will be T34. Now we need to set the string of the joint. The joint was, let's it T XX 21, let's use A for this case. So if inside this joint, inside this tool assembly, there's a joint name like this, let's say equal true, then let's say that the IL substation number, if that the IL substation number equals 21. And that would be it. I did not say end if, but enif. Okay. Let's generate G code and see what do we get. Okay. Again, we were going to go with ray 0 because we just need to see the output. Okay. Here is the channel 1. And as I said, 21. So how it is working? It is going inside this procedure and saying, okay, I found this joint. So for this joint, is the substation number 21. And then it is adding that number to the 3400 that we had without this. So it is 3400 plus 21, so T34 substation 21. Now we also need it for the wear offset. So here is the, okay, here is the wear number. So if it's turning, it's not turning for us, it's milling. And let's say if, oh, sorry, let's copy this one. If the substation number, let's say, is not equal 0, so we have a multi-tool holder. Let's say that I will duplicate this line, move it up, that the wear number is equal to the substation number. Else, it is equal to the D offset that was used before. So end if, let's save it and let's see what we got. Again, generating for the same. Again, we're going to be using trace 0. And let's see the result. Okay, let's go down. Here it is T3421, and here we have the wear offset. Now let me check if I did not close the previous one. Yeah, I did not. So we got the station number, but the wear offset was still 34. Now let me close all of these windows, and just if you want, you can go and just copy this, because for other station numbers we would get an error or a blank spot. So I will call this 1, 2, 3, 4, 5, 6. Let me just format it and say 21B, it's still 21. 22A would be 22. 22, 22B, also 22. 23A and 23B. So that would be it. I can set this like this, so it's prettier, and that's it. If I generate for any other operation now, see, these are all on T34. You can see this is the same tool, but this one is not the same. So we should expect a different substation number. Let's generate for this one. We have implemented the logic for the whole multi-tool holder. And let's check if the output is correct. Now, please note that you should know which holders are used so you can handle the joint numbers. But let's check. So here it is, 22, 22. And that's it. Thank you all for joining us. You can post your questions in the forum, and that will be it from my side. Thank you. I will cut back to Daniel.
Wonderful presentation, Vukasin. Thank you very much. Hope everybody enjoyed in this webinar, part 3. I would just one thing, Vukasin, I noticed, that in the one get function, get component's name, Vukasin talked about additional parameters, if it's 0 or if it's 1. Guys, if you're trying to generate this a get function in the current official version of SP3 hotfix 1, you will get an error message. Of course, this is still in the development version, so with upcoming hotfix or SP4, this get function will work accordingly, okay? And with that being said, thank you again for joining us today, and see you in 7 days again. Take care and have a great weekend. Bye-bye.